Let's find the dimension of electromotive force together. Most people are familiar with dimensions that involve masses, length, and time. And that's the most common dimension that people are familiar with. But when it comes to EMF and then whenever it involves other fundamental quantities, they're not quite familiar with that. So how do we go about the dimension of electromotive force? The first thing we need to note is that EMF will have the same dimension as potential difference. So because we're familiar with potential difference, so I'll be using them interchangeably in this video. We know that potential difference can be calculated with, so it has a lot of relationship with so many other quantities in physics as well. For instance, potential difference is the product of the current and the resistance. Power, electric power, now this P represents electric power, is current multiplied by the potential difference, which is V in this place. And work done as well, work done by a charge is QV, which is Q is the charge and V is the potential difference. So there are so many other relationship with potential difference that we can find. So but what we're looking for here is a more convenient one that we can use to manipulate our way around to isolate this potential difference and get what? And get the dimension. So I'm going to be using this particular guy. Work done equals the charge multiplied by potential difference. Of course, if you remember very well that charge is the product of current and time. So I'm going to be using that very soon. So the idea of dimension is that we need to break all these things down into fundamental quantities. Once you have been able to break anything you are working with down into fundamental quantities, then you can easily find their dimensions, because dimensions actually belong to the 7 fundamental quantities. And the easy way to do this is that you don't want to be playing around most of these fundamental quantities too much. All you need is their SI unit. If you can write any quantity as a combination, as the unit of any quantity as a combination of the SI unit of the fundamental quantities, then you can easily find the dimension. So, and that's what I'm going to do here, and I'm going to show you. Now, let's start with work done. We know that work done is force times distance. Of course, there are so many things that we can talk about here, but dimensionally, we can do anything that we like. So that is force times distance, that is work done. Then I extracted this QV, which is current multiplied by time, then V being the potential difference. Now, force again can be broken down further into mass times acceleration, mass, acceleration, then this distance just follows suit like that. And we still have current multiplied by time. And then the PD, which is what we're looking for, its dimension. So I'm going to be isolating this guy on the right hand side. I'm going to be getting the unit of mass is kilogram, unit of acceleration is meters per second squared, and the unit of distance is meter. Also, unit of current is ampere, and unit of time is second. So what I'm doing now is that I want to get rid of all of these quantities. I just want to work with their unit. So I'm going to be working with their unit, because with the unit, it is easier to get the dimension. And so all I'm going to do now is I'm going to take this ampere and seconds to the other side. That will be dividing both sides by ampere and second, the product of ampere and second. So here we then have combination of kilogram, meters per second squared. Then there's meters here divided by ampere multiplied by second. That will be equals potential difference, which is volt in this case. So I've isolated the unit now, such that anything I have here will be the unit of the volt in SI unit. That is unit of combination, unit that combines all fundamental units together. So in this place, we can do a little bit of blending together. We can see meter here, we can see meter here. That will definitely multiply together and give us meters squared. So you can see it here. Then we can see second raised to -2 here, and we can see second here as well. So if you blend that together, that will be -2 minus 1, and that will give us a -3. So that is what we have here. And then of course A, because here it's like we have the inverse of A, 1 over A, which is 1 over ampere. So that's ampere raised to -1. So now we have a combination, that is the unit, which is volt, as a combination of SI units of fundamental quantities is this: kilogram meter squared per second cube per ampere. So this is the unit of volt. This right here is what makes up volt. And since we have this, we can now find the dimension. Now, from the table being displayed on the screen, you can screenshot it for future reference. So you can see the unit of each of these fundamental quantities and their corresponding dimension. So you don't really need to stress yourself about the quantity themselves. Just whenever you see this, any of these units, know that they will correspond to the dimension that follows. So with that now, so if you use that table, I believe you have screenshotted it. I'm taking it away now. Now, you see that kilogram is capital M, meters is capital L, so it has a power of 2 here, so we have 2. Seconds is capital T, so we have T to the negative 3, and then ampere is just going to be I, so that's a mistake. Let me quickly correct that. So that's it. Yeah, that will be the correct dimension, and that's it. That's how you find dimension of electromotive force. So if you have similar quantities like that and you want to find the dimension, you just need to play around it with the way I've done. So if there's a dimension of anything that you've been having difficulty to find, you can let me know in the comment section. Maybe I'll make a video for you. I'll see you around.